I'm Jake, one of the senior geoscientists here at ELISE. In today's video, I'll be covering the automatic fault extraction module. Let's get started. I'm going to go over a few slides just to talk a little bit about the background and the theory behind the automatic fault extraction workflow. Then we'll jump into a live demo where I'll show you all of these techniques in action. We start by giving the software some seismic data. And by starting this process of the fault plane creation, the software will create a structure-oriented filter and create, in the background, it will create a variance cube. Now, we don't have any control over this at this point. This is kind of a black box operation. But the variance cube is first created because the technique uses a tensor ellipsoid that we will design to scan that variance cube. And what it's doing is looking for the maximum degree of variance, which is correlative to what we would call our fault plane maximum. Think of the fault plane as like a fault probability cube. Once we have the fault plane or fault probability cube, we then take it to the next step, which is to create a fault thinning cube. The fault thinning cube is created by taking the extreme probability values from your fault plane within a specific window that we'll design to keep only the highest probabilities within that window. The rest of the volume is considered a null set. It is from the fault plane thinning cube that we then extract our faults. So that's step 3 of this 3-part process, but we're not typically done yet. Once we have the faults extracted from our fault plane thinning cube, we'll want to edit those faults, not only manually, but also filter them so that we can create subsets of faults so that we have exactly the type of faults that we want to use to constrain our geomodel, constrain our model grid, or just use for display purposes moving forward. Let's take a more in-depth look at each of these steps and give you a little bit of information on what the software is actually doing. So for the fault plane cube, the software is going to take the entire seismic cube and it's going to start reading your seismic volume at the first voxel, the first sample, and the first trace, right? So we're going to design this ellipsoid scanning disk by giving it a range of azimuth and dip to scan through. We'll also design the disk to be a certain length vertically. So this is all dependent on the type of faults that you're hoping to extract from your volume. I'll talk a little bit more about those considerations in the live demo. Once the software scans that variance cube and finds the local maxima, it'll save that value for that considered voxel and move on to the next sample. It'll do this for the entire volume, and the output will be this fault plane or fault probability cube. Once you have your fault plane cube, we'll use that as an input to create the next part of the AFE module, which is the fault thinning cube. The fault thinning cube uses the fault plane as the input, and then using a Hessian reduction, it's going to search across a specific window size and look for the steepest gradient or the steepest or the fastest degree of change from high probability to low probability. It'll then save that value and move on to the next trace or the next sample. There are multiple methods for doing this, and the method you choose will be based on, of course, your data quality and the type of faults you're hoping to extract. Hessian is one method, but we also have a direct method that is more designed toward larger continuous faults. And like I said, I'll talk a little bit more about that in that live demo. Once we have the fault thinning cube created, we now want to extract faults from that fault thinning cube. And there's a number of parameters that we're going to talk about when we create or when we set up the fault extraction process. And I feel that's the real spot where we can really hone in on what we truly think are faults and start to filter out even further things that are probably just noise or false positives. The Hessian method for creating the thinning volume is going to be more directed toward higher degree of resolution. So in places where you have polygonal faulting perhaps, or where you've got a known developmental area, typically we'll see folks using the Haitian method there. The direct method, like I mentioned moments ago, is really more geared toward larger controlling faults. It'll be more continuous, which has its ups, but it also has its downs. We'll talk a little bit about that in the demo. Now, once we've got the fault thinning cube created, that the next step, of course, is to then extract the faults from that fault thinning cube. So this process is very similar in some ways to the way that we build our model grid, where we allow the software to scan the seismic and create small little patches and then merge those patches to create much larger horizons. Much in the same way, we use this same technique for the fault extraction. We take the fault thinning cube and the software goes through and it creates these small minuscule patches of fault bodies that are then merged together. Now, we have a really unique option that I'll show you guys where we can tell the software to go through and actually do an auto merge or a second pass through to try and merge more of the faults together. I'll show you an example of what faults would look like with and without that auto merge option being turned on. So here's just a quick example in pictures of a bunch of faults that were created without the auto merge algorithm applied. And that would be on the left-hand side here, where you see some of these faults are pretty obvious to you and me that they should be together, but at some point the planarity was just outside of the range that the software was acceptable for that first pass, so it didn't connect them. However, using that auto merge function, the software went ahead and connected a lot of those faults. So this can be a really handy tool, and again, I'll highlight that once we get to that demo. We have the ability to look at merging faults in both the time and in the inline or crossline direction. And that auto merge function is going to work not only in the time, but also in the inline and crossline views. Now, once we've got our fault set all put together, we can have something that looks a little bit chaotic. Sometimes that's just the nature of your seismic. Thankfully, what we can do is filter out or use the dip and azimuth filter to go through and fine tune only the direction or the strike and dip of the faults that I want to keep within my fault set. I also have the opportunity to filter on size, so we can reduce the amount of faults based on size, dip and azimuth, and then create a brand new set based only on the faults we truly want to keep. All right, let's go ahead and jump into a live demo. Okay, let's get started. You can find the AFE module in two places. To access the AFE module, you can start in the fault toolbar in your module selection toolbar. If you go about halfway, just a little past halfway down, you'll see the icon that says AFE. If you click on that once, you've got three options. Again, this is a three-part process, and so we would start from seismic as the first option. Now, the other place you can find this attribute is under your volume tab in the attributes icon. And so these are attributes that we're going to be creating, and so you can start this process off from your attribute pane or from your fault toolbar. So I'll just go ahead and click once on the AFE fault plane and say OK. And that's going to open our attributes computation window. I'll drag and drop my seismic into the input parameter. And now the software is using that as the input. I'll just focus in on this faulted region down here. Now here's a quick little pro tip that I think everyone would really benefit from. So I like to tell everyone about this. And so what we're going to be doing is manipulating different dip and azimuth as well as scanning disk size ranges, right? So what we're doing is we're trying to optimize our parameter selection to highlight the faults that we truly believe are actual representations of faults, and we're trying to leave as much noise as we can behind. So one thing I like to do is start by opening more than one fault plane. And the reason we do this is we'll be able to jump back and forth using a preview to kind of get an idea on which set of parameters are working best for us, right? So I'm going to just set a focal point here. Now on the right-hand side, we've got some parameters that are going to be affecting this scanning disk. So that's what we're doing now, is we're actually creating or designing this ellipsoid disk that's going to scan our seismic to create our fault plane volume. I'll let this first one default from 70 to 90 with a range of 0 to 180. I'll leave my disk weighting method as a Gaussian, and I'll also leave the default for the disk size. Now, because I set a focal point in this pane, by switching over to my other pane, that focal point will be in the same spot. Now, I'm going to alter a few things here by interacting with this filter. So instead of leaving my azimuth full 180 degrees, I'm going to just grab this and I'm going to say, I only want you to find faults that are essentially trending north-south over about a 60-degree range. I'm also going to ramp up or change my Gaussian to a flat. Now, this is going to allow the software to run a little bit faster. The description of the differences are just right here. And I'm going to I'm going to reduce this actually to look for a little bit smaller faults. Now, the beauty of this method is that by clicking on each of these tabs and saying, show me a partial preview, I'll be able to bounce back and forth between each of these tabs to see which one is giving me the best output. So I'll click on partial preview here, and that's going to run, and it's going to update and show me a preview. Okay, that updated, and now we see a preview of what this set of parameters would give us if we were to move forward with this fault plane job. So I'll switch to the other tab and do the same thing. Okay, now that's finished. Now what we can do here is quickly jump back and forth between the two tabs, and you can see very quickly I believe that's going to be that first tab. So what I'll do is close that second tab, right? Because if I click run right now, it's going to do both of those in sequence, and I only want to save the one that has been optimized. I would then click run. Now I've already created a fault plane just for the purposes of this demo. I'm going to start by moving back to the fault toolbar, right? So we've got the fault plane volume created. Now I'm going to go and start the second step, which is from fault plane. So the fault from fault plane is looking for, is going to be to create the fault thinning, but it's using the fault plane as an input. So just like I did before, I'll set up another tab. I'll use the fault plane as an input. And I'll use the same technique. So I've got two different methods, the direct and Haitian method. So for this first tab, I'll leave as direct and a window size of 3. For the second tab, I'll change it to Haitian and leave that window size of 3 as well. I'll set a focal point so that we're looking at the same spot in both windows, and I'll run partial preview. Now this is going to go a little bit faster, so I'll let this run. The fault plane, just FYI, the fault sort of processes within the software, and so it's going to run for a while, whereas the fault thinning runs much faster. So now you can see we've got very obvious differences in the output. The Haitian is much more disconnected, right, because it's more sensitive to vertical discontinuities than the direct method. So the idea here is, again, you would just decide whether, well, actually in this case, what I would do is say, well, do I like the direct or Haitian more? I'm going to decide I like the direct for this. Other tab and increase the window size, right? So now I'm just trying to decide, I've already made the decision, I like the direct method, but I'm not sure that that window size of 3 is really the best for me, right? So maybe I can improve upon that by increasing the window size. And it looks like by increasing that window size, you see I was able to get rid of a lot of that noise that we still see by using a much smaller window size. At this point, I'll decide that my second tab was the better set of parameters to move forward with. I'll click run, and the eventual output is the fault thinning volume. To complete this process, I'll say from fault thinning. So I'll go back to my fault toolbar, and I'll say from fault thinning. The input box here is now looking for the fault thinning volume as an input to extract my faults from. And here we come to the really, really great place where we can really start to filter out some of that noise that we've still seen propagated through the first two processes. So the minimum dimension is in regards to the actual size of the fault, right? So this is an area calculation. So it's the maximum amount of pixels, of interconnected pixels, to make up a fault. So increasing this number would mean you're only creating or keeping large faults. Decreasing this number means that you're allowing yourself to create much smaller faults, right? And again, this is a aerial computation, and so it's the max number of connected pixels is not necessarily a vertical calculation. The second parameter here is the minimum thinning value, and this is, I think, one of the main keys to really focus on in order to extract only the very high probability faults. So if I zoom in very closely here, I'm going to find one of these areas. Okay, here we go. The red is indicating a very high probability. The blue is kind of the lower probability. And if you follow my cursor, you'll see down in the lower corner of my window here, there is a value, and it's right now it's -999, and that's the null value. Now, if you keep your eye on this value here, as I move my cursor back into the window, you'll see that value change. If I place my cursor on a blue colored, you'll see that that value is now 0.016 essentially. So it's a very low probability value. If I place my cursor in the red, you'll see that changes to 0.05, one of the much higher value probability values within my thinning volume. So what I need to do is decide where between those two values I want to stop the software from creating a fault. And so I just have to make a judgment call essentially. And this takes a little bit of back and forth to get the right value. And so if I place my cursor here, I see a value of 0.029. I think that's a little high, so I'm actually going to just change this to 0.025. If I want, I can increase some smoothing. So this can sometimes help the software on that initial merge to smooth some of those out, to decrease the rate of change of planarity from one patch to another. So this can sometimes help your faults be more continuous. And then here's that auto merge option I was talking about. So I'm going to leave it off for this first example, and I'll click on partial preview. And this is going to open a 3D window and just show me a preview of some of the faults that we would create using these parameters moving forward. And if I look at my 3D objects list, you'll see that the preview has just created 15 faults. Now, if I were to tile my windows, I'm going to close that 3D window, open that up. I'll go ahead and turn on my auto merge now and run that partial preview again. Now, okay, so in this case, the software wasn't actually able to find any faults that it felt would be beneficial to merge together. You see, I still have 15 faults, but in the real world, by turning on that auto merge option, it is very likely that you're going to see a reduced number of faults here because the software was able to actually merge some together. At this point, what we would do is say, go ahead and run this job, and the software is going to create your faults for you. So I'll go ahead and open up a fault set that I created. Let's do these guys. So I'll just go ahead and drag and drop these into my seismic or my 3D window, and you'll see I've got a number of faults. You'll see I can reinitialize that filter, and now you see a few more faults pop up, right? So this is a spot where we can filter out and remove certain faults from the view. So it's not taking them away from the fault set, it's just removing them from the 3D view. All right, so let's say I wanted to create a set of very, very specific north-south trending faults. I'll set my dip azimuth filter to a dual azimuth direction. I'll grab this yellow tab here. I'm going to spin around, and I'm going to create this shaded area is going to show me the faults underneath the shaded area. So you can see in this dip azimuth filter here, the green dots indicate faults that are being shown in the visualization in my 3D window. The gray faults are faults that are within the fault set but are being hidden by my filter. I can do one more thing. Beneath this is the size filter. So on the left-hand side, you have the smaller faults. On the right-hand side, you have the larger faults. By placing my cursor in this shade, in this kind of coral colored region, holding down mouse button 1 and dragging that over, I'll start to eliminate some of the smaller faults from my view. And if you keep an eye on that 3D view, you'll start to see some of those faults disappear. Okay. I'll say at this point, I'm happy with the filter that I've created, and I like this fault set, and I want to keep it. What I can do is click on the Save Fault Set icon. It's going to ask me a question, which I think is really neat and really intuitive. The software recognizes that you have a fault set open that contains more faults than what we're seeing in this display, right? So it's saying, well, do you want to save all of the faults that are in the fault set? Perhaps we've manipulated or edited some of those. Or do you want to just save this as a new fault set and only the visible faults? And so in this case, I'll say I want to only save the visible faults. We'll give it a quick name. I'll just call this test. We'll say OK. Now, if I remove all of my objects from my 3D window and I drag and drop that test in there now, you'll see it has only the faults that were visible when I save that. Now, let's go one step further. I see a fault here. Well, there's 3 faults, and I think those are all actually maybe part of the same fault that just the software didn't put together, wasn't able to merge. Let me show you how to really quickly merge faults together. With the mouse mode on the selection mode, I'm going to double click to select one of the 3 faults to merge. I'm going to now hold down the control key and double click on the other fault, and I'll do the same thing for the 3rd fault. So I've selected the 3 fault segments that I want to include in this to merge together. And all I have to do is click on the plus sign, and that's going to merge those faults together really quickly. Now, by default, when you merge a fault together, it's going to show all of the picked points in the display. Now, if you don't like that, that's okay. We can turn that off pretty quickly by selecting that fault and interacting with your properties pane. If I come down to show picking and turn that off, you'll see I can turn off those pick points. And now that fault has been merged into one fault. And we got to do one more thing here. And because I've edited this, I need to save this. So I'm going to select this fault, and then I'm going to do a Control A to select all the faults in that view. And now I'm going to now save that as its new fault set. I'm going to overwrite test. If I remove that now from my 3D objects list and then drag and drop that back in there, you'll see that merged fault now exists as one single entity. That's all I wanted to show you for today. I'll say thank you so much for checking out this video. As always, if you have any questions, please send an email to our general support inbox at support@elise.fr. We'll try and get back to you as soon as possible. Thanks again for checking out this video, and we'll see you in the next installment. Cheers.